Hello everyone, welcome to last lecture of this course. In this lecture, I will talk about deep learning and PyTorch. PyTorch is a library that you can use to implement a neural network for deep learning. And it might be useful for your research or other courses that you want to get in computers. In this lecture, I will talk about deep learning, and you have probably heard the term deep learning before. And actually, deep learning is a state-of-the-art model in many data science and machine learning application, and can be so useful because actually it can generate lots of interesting output based on the task. And deep learning use the large, very large neural networks. And if we want to know about something about deep learning, we should know about the neural networks. And neural networks are a type of machine learning model, and we want to discuss today about this. And after that, I will talk about the PyTorch, which is the library for deep learning, and that can be so useful. And another library for implementing deep learning is TensorFlow, and both of them are so popular in computer science, but they are also kind of similar. But I think TensorFlow is actually more complicated than PyTorch. And if you want to implement a code in deep learning, PyTorch can be more easier. And the first question is that what is neural network? And actually, in neural network, we have some layers that are connected, that are fully connected to each other. And in the first layer, we have input layer. And in the last layer, we have output layer. And between them, we have hidden layer. So between input layer and output layer, you can have lots of hidden layers, but it's dependent on the task. Actually, you should decide about that, how many hidden layer you need, and how many actually hidden unit you should have in each layer. This is the hidden unit, and consider that we have a data point with some features, right? So for each data that we have, we can have a feature vector that we feed this feature vector to the input layer. And at the middle, we have some hidden layer that are fully connected to input layers. And finally, we get the weights in the output layer and decide about the output. So as a simple example, you can consider the classification, and consider that we are getting a sentence and we want to know that this sentence is positive or negative. So we just need to convert the sentence to words, and each word has a numbers or ID, and then we can have a feature vector for the sentence, and then feed this feature vector to input layer, and then in the output we are going to train the networks to generate the true label that we have. For example, if we know that the the label of this sentence is positive, we can train the network to generate the, for example, 1, and for negative -1, right? And another thing that you should know is that you can consider each hidden layer as a matrix, because we are getting a vector and we want to convert to another vectors of weights. So for example, if we are getting this x1, we can multiply x1 to each weights that we have for first hidden layer and generate the outputs. And also another things that you should know is that for after multiplying the input layer to hidden layer, we have a nonlinear function on the output of each hidden unit that we have here. So at the most basic level, a neural network is a model for mapping inputs to output, like linear regression, right? So we are getting the input and we want to generate the output. So these networks can learn how to generate the output based on the input, right? And it has parameter which we choose to minimize the loss on the training data. So parameters are these weights that we have for the hidden layers and that we want to learn them. We can call them weights. So unlike the linear regression, there is no closed form solution for the optimal weights. So if you remember, we can have a closed form solution for the linear regression, but here we don't have any solution for that. And actually we have solution, but we don't have a closed form solution for that. And training a neural network means that iteratively updating the weights to obtain a smaller and a smaller loss on the training data. So we have some training data and we want to generate these weights here that minimize our loss for generating the output based on the input that we have in the training data. And the parameters of a neural network are organized into layers. So if we just have one hidden layer, the parameter that of our neural network can be used for just one, can be organized for just one layer. We can have more than one layers, but it's completely dependent on the task. And there is usually a nonlinear operation applied between layers. So we have this nonlinear function that immediately after getting the output of each hidden unit, we apply that nonlinear function to make it more flexible to generate the output, because we don't know, we can have a linear model to map the input to the output. So sometimes, in most cases, actually, we need to have a nonlinear function to map inputs to the output. So because of that, we are using this nonlinear function over each unit, each hidden unit. And you feed the input from the first layer and apply a nonlinearity and feed that to the second layer if you have. And typically we refer to any layer before the last layer and as a hidden layer. So every layer that we have between input layer and output layer are called hidden layer. And So as I mentioned, the output layer, actually the final layer that generates the output is called output layer. So let's see an example, a simple example of that, but by a feature vector that we have two features for one input, and we have two hidden layer and an output layer. And for the first hidden layer, we have three hidden units, right? And for the second one, we have two hidden units. And as I mentioned before, the number of units in each hidden layer also is completely on the task, completely dependent on task, and you can decide about that. You can have 3 or 2 or 300, it doesn't matter. As long as you are getting the better result, you can change the hidden units in hidden layer. And this f function is the nonlinearity function that I mentioned that we have over all the hidden units. And by getting x1 and x2, we multiply each weights that we have for each unit, each hidden unit. And we also have a bias here. And for the second hidden unit, we can generate the output based on this. That we have different weights, but for each feature that we are getting from the input. And after that, we have the output of the three hidden units is the first layer, and generate the. And we want to have another hidden layer here by different can have different nonlinearity function on the output of each layer. And as you can see, we have different weights for this hidden unit in the second layer. And also we have a bias here. And finally, we are getting the output of these two hidden units in the second hidden layer, and we generate the output based on another nonlinear function and weights that we are training them, we are learning them. And all these weights that I mentioned are actually we are training them based on the training data, right? If we know these weights to minimize the loss function, that would be great. So, for example, consider that we have lots of input and we are training them based on the loss function over all the inputs. So if the neural network can get all the inputs and then generate exactly the output that we expect, that would be great. So that's why we are training neural network to minimize the loss function. And the loss function is based on the output of the function, the output of the networks and true labels that we have. So we want to generate this output in ideal case, exactly same as the label that we have for this input, right? So you can also think of each layer as a weight matrix and bias vector. And this is because for this layer, you can think of, we have a matrix for the weights and bias that the matrix is actually the member of matrix are W11 and W21, W12, W22, and W13 and W23, right? And we have also three biases. And we can consider the bias as a vector and the weights as a matrix. And multiply input by the weight matrix that we are trying to do that here, and add the bias vector that we add them. We just need to add this bias vector to the multiplication of the input and weight matrix and apply element-wise nonlinear function. because of this function that I mentioned here, which is a nonlinear function. So we just need to apply a element-wise nonlinear function on the output of these two steps. So if we consider that we are actually we think that each layer as a matrix and the bias vector, we can get the vector from the input, which is this one with two features. And for the first layer, we have a matrix that we want to multiply this to x vector and plus that to bias vector, and then apply a nonlinear function. Then we generate some output, and for the second layer, we have another weight matrix and another bias vector, and we are getting the output of the first layer, which is H1, and then multiply that by the weight matrix of the second layer, and then plus that to vector of bias. And finally, we have another weight matrix for the output, and then get the output of the second hidden layer, and generate the output. So I think we also should have another bias here. This is a typo, that we have this bias here, and we just need to add the single number because this is not the vector. And finally, we have another nonlinear function on the output, and we get the output of the network, and then try to minimize the difference between this output and true label that we have for this. So let's see how we can do that in Python. I'm not talking about the PyTorch right now. I'm just talking about how we can do this multiplication on the Python, actually in the NumPy. So consider that we have one row of input from a feed-forward neural network. And we call this kind of network that we just feed the inputs and get the output based on the fully connected units. Feed forward neural network, which one, and we just have one hidden layer, right? So we get the X, which is a vector, and we have three features, right? For the first hidden layer, we are trying to defining a weight matrix, which is we just randomly initialize that by normal distribution, and the size of each dimension is for the first dimension we have 2, and the second 3. So here the hidden layer actually maps input with three features to hidden representation with 2 values, because first vector that we have for the X has 1 by 3 dimensions. And for the hidden weights, we are trying to convert these 3 features to just 2 values, right? So if we want to do that, we need to transpose X and then multiply the hidden weights to X transpose. X transpose is 3 by 1, and if we have 2 by 3 for the hidden weights, 2 by 3 and 3 by 1 generated 2 1 by 1. So this means that we are actually maps 3 features that we have to 2 values, right? And we have we can have some bias here, but I didn't add them here. But after that, after generating them, you are doing this part of code, and you can have another vector that is bias, and then try to add that to this actually vector, and then we can apply this nonlinear function on the output of this, and we just need to use a function from a mass. Mostly, you can see that mostly people use this function, but it's not necessarily. But actually, if you use this nonlinear function, you can get better results. And finally, we have two values for the first input that we get, and now we want to generate one single value for these two features, right? So if we want to convert these two features to one values, we need to have another weights, which is this one. And because we have just one layer, we are ignoring this part. And so we get the weights for the output, which is 1 by 2, and then because we have 2 by 1, if we multiply the 1 by 2 to a transpose of this hidden layer, which is this is the 1 by 2, and this is the 2 by 1, and then the multiplication of them can generate just 1 by 1 values. And also we have another nonlinear function on the output of this multiplication, and as output we have just single value. You can have for example, 2 values or 3 values for the output. It just completely dependent on the task. For example, if you have a classification on 3 labels, you can actually the output can be 3 real values that show the probability of assigning the input to one of these 3 labels that we have for the classification. You can find lots of examples of neural classification or other task in PyTorch or TensorFlow that generate different output. And also, if we want to extend this example to have more than one input rows, for example, if you have 50 inputs, if we want to extend this actually this example to have more than one hidden layer, how we can do that. So in this case, instead of just getting one vector for the input, we are getting a matrix that the number of rows is 50 and the number of columns is the 1000. So 1000 means that for each of these 50 inputs, we are getting 1000 features, right? And so after that, we have 2 hidden layer and the output layer, right? So for the first hidden layer, we are actually we are downing these 1000 features to 500 features. And after getting these 500 features, hidden features, we are downing them to 100 features in the second hidden layer. And finally, in the output, we are downing these 100 features to just 2 features for the output, right? So if we want to have the operation for the first hidden layers, we just need to multiply the hidden weights for this one to X transpose, and then this can generate 50 rows and 500 columns, because we are downing 1,000 features to 500 features, right? And for the second hidden layer, also you can add a vector for the bias here for this one that I mentioned here, but I didn't add that. I just want to show that how we can multiply the metrics to generate the output of each hidden layer. So for the second hidden layer, we get the output of the first hidden layer and transpose it and then multiply it by the metrics that we have for the second hidden layer. And we also have another non-linear function on that this can generate actually 50 rows and 100 columns, because we are downing this one to 100 features, hidden features. And finally, we get the output of this and transpose it and then multiply by the weights of the output. And also we have another non-linear function, and then generate for each data point that we have in the input, which are 50 rows. And we are generating 2 columns, means that we have 2 features for each input, and we can get these features and compare them to the true labels that we have for the rows, and then compute the loss and update our network. That I'm going to talk about, that how we can do that. And there is other architecture for neural network. The neural network that we talk in this lecture are feed-forward neural network or multi-layer perceptrons. And but there are other kind of neural network based on the architecture of them. And I just mentioned some of them here to introduce you to them and introduce them. And for example, we have recurrent neural networks, and these recurrent neural network actually are useful for the sequential data. For example, for the text, you are getting some words, and the position of the words are important. So if we want to consider the position of words in a sentence, you can use a recurrent neural network. And in recurrent neural network, we have just we have identical cells that are applied to the input again and again and again, and the output of the one cell is the input of the another cell. And the convolutional neural network are another famous architecture for the neural networks that apply mostly on the computer vision and image. And they have small filters that call convolutions, and these small filters can apply over each section of the input, and then try to extract features, extract the representation of each sections. For example, if you have an image, the convolutional network can be so useful. And another one is transformers that use attention. Actually, they are using the attention, which means that they consider different weights for a section of, for example, sentence, and try to actually amplify a certain part of the input to each layer. And they are actually the transformers networks are a state-of-the-art model in natural language processing, if you are interested. And so I talked to the architecture of the neural network, and now we want to know that how we can train this kind of networks. And the training process looks like this. And if you want to know more, then you can use this link. And at the first, you need to define the neural network architecture, and then you need to initialize the layers of actually the weights of each layer. And for each input output pairs in dataset, I mean by the input means that the features, and the output means labels that we have for that input, right? So we need to feed the input to the network, and then we need to compute the loss. So we are feeding the input and getting the output from the network based on the weights that we just initialize and the architecture of the network, right? We get the output and then compute the loss, which means that how far network outputs from the true output. Just compare the output of the network with the labels. And after that, we get the loss, and we want to compute the gradient of the parameters with respect to the loss. We just need to find the gradient of each weights that we have in the networks based on the loss. Now we want to know that how update the weights that we have in the network. So if we just have one, if we just consider one weight, we can update that by this formula. Or there are lots of other actually methods for updating the weights in the network, but I'm not going to detail of them. I just mentioned one simple of that you can update the weights based on the hyperparameter learning rate and the gradient that we just compute based on the loss, right? So for each weight, we just update the weights based on this formula. And the learning rate actually is the rate of the updating the weights in the network. If you consider a large learning rate, that can be so bad for the training because the network cannot learn in this rate. If you just consider a small learning rate, very small learning rate, so in this case the network, the learning of the network can take lots of time. So you need to decide about this hyperparameter learning rate for your network. And after that, we can do this for actually for loop for each data each input, lots of time until the loss function actually converge, or you decide that okay, now I'm satisfied with the evaluation measure that we are care in your task. For example, in a task, if you get the accuracy of 50%, that would be enough, and then you can just stop your training. But the number of actually, if we have another for loop on this, we can call them epochs, and then for each epoch, we just need to feed all data that we have to the network and update the weights in the networks. After training, your model can predict the output for the new inputs. So if you train your networks, you can stop the training, and then you have a networks that can generate output based on the loss function. So you just need to feed the new inputs and get the output. And we can also use for the training. We obviously we use the training data. For the test set, we get some prediction after training and see if they are right on based on the true labels that we have for the test set. And in this course, I just need to show a simple example to implement the neural network and training the steps in PyTorch. And I think that would be useful to just start working on a PyTorch or TensorFlow because they are so useful in the data science. And if you want to continue on the data science or machine learning or computer science, I think these days you have to know about the PyTorch and TensorFlow. So that would be a good start for you to start working on PyTorch and deep learning, and or also you can if you familiar with the PyTorch, that would be good to start working with TensorFlow. So what is the PyTorch? PyTorch is actually is a layer over NumPy that allows for fast, flexible neural network implementation. And you can find many standard neural network architecture and training algorithm. And you just need to write 2 or 3 lines function call to implement them in the PyTorch. And also, if actually I'm not going to detail of the GPUs, but as a simple introduction for the GPUs, if you want to have a huge neural network, lots of parameters, lots of layers, that would take a lot of times to train on a data set. So GPUs are using PyTorch to actually make it faster to train a huge neural network. So if you can find a machine that have GPUs, you can use the GPUs to actually make it faster to train a huge neural network. And you can also compute all gradients and apply gradient-based update with a few lines of the code. So in summary, the PyTorch is so flexible, and you can use that easily. That's why the PyTorch is more powerful these days. And in a basic of the PyTorch, we have tensors, as we have in a NumPy. The basic actually data type is array, and in the PyTorch is tensor. So we can just compare them to make it easier to find out what is the tensor. Also, you can create a tensor with command similar to NumPy array. That would be easy because we are already familiar with the NumPy. And it's easy to convert back and forth between NumPy arrays and tensor. So if you want to just generate one single tensor, you can, at the first, you need to import torch, and you can call a function once that we already have in the NumPy, and pass a number of elements that we want in the output. And this can generate one tensor, and each element has a value of 1. And you can multiply that by 7 and then generate the output. And as I mentioned, you can actually convert tensor to NumPy arrays, and also you can convert NumPy arrays to tensor. So if we want to use PyTorch to train a neural network, how we can do that? At the first, you need to define a model. And so well, there are lots of ways to define a model in PyTorch, and some of them are flexible and easier, and some of them are not. But the simplest one that I want to mention in this course is the torch.nn.sequential. And in this actually function, you can pass the layers that you want and the non-linearity function that you want, and then exactly the order that you want in the output. So you should actually, if you want to define a neural network model in PyTorch, at the first you need to define number of layers or layers that you want to have in the neural network, and the nonlinear function that you want to apply in each layer. And also you need to define the exact order of the layers that you want in out, right? So let's see an example that would be more clear for you. For example, we are defining a model. At the first, we are importing torch.nn as an nn. And we are defining a model based on this function that I mentioned here, sequential. And for the first layer, we are defining a linear layer with getting 1,500 for the size of the units that we have in this linear layer. And then we need to apply a nonlinear function on this hidden layer. And then we have another layer here, and we want to apply a different nonlinear function on the second layer that we are defining. So after defining the model, we generate an input. Actually, we are defining 3 data points with 1,000 features for each one. And if we call a forward function and pass x, which means that we are feeding x to these neural networks. And also you can call model and parentheses and x to feed the input to the networks. And these 2 lines are the same. And so now you see that how we can actually easily define a neural network in PyTorch, and then feed the input to the networks. And each linear layer includes weights and bias. You don't see them, but the torch actually initialize the parameters of these weights and layers for you. So we just need to define the layer that we want and the nonlinear function, and then in an exact order that we want to have in the networks. So we are getting 1,000 and then downing them to 500, and then getting the 500 to downing to output, right? So many loss functions are implemented as an object in PyTorch, and you initialize them before training and take a tensor of the predict output and a tensor of true outputs. and return a single loss value. So because we define the networks and we feed the inputs, and we are getting the output based on the networks that we just defined, right? So if we get the output, which is the predicted output, and then a tensor of true outputs, we can compute the loss function. There are lots of loss function. One of them is the mean square error that we can get from torch.nn. And if you call nn.msp loss, you are defining mean square loss function in the torch. After that, we define a simple model by nn.sequential and passing just one hidden layer with these values, with this actual size. And we define a input which has 50 data points. And for each data point, we have 5 features. And also we have true labels. We are defining that for each data point, we are defining just one output that we expect from the networks. And after that, we just need to pass the input to the model and then get output. So based on the loss function that we define here, we just need to pass out predicted output and true outputs to the loss function and get the loss function. And if you print the value of the loss function, you can see the loss that the network generates. This means that the output of the model is different than the true labels by this loss function, and because we already defined the loss function based on the mean square rule, this is the positive value. And so now we got the loss function, and we want to train the networks based on this loss function. As I mentioned here, we compute the loss function, and now we want to compute the gradient of the parameter with respect to the loss function and update the networks. And then if we update the networks in the second iteration, we hopefully get the smaller loss function, because we are updating the weights to get a better output. So it's so easy to compute the gradient for all parameters with PyTorch. How we can do that? So we get the loss function, we define the loss function, and then get the output of the model by passing the input, and compute the loss function by passing the output, predicted output, and true labels, right? And MSE is actually our loss. And if you call backward parentheses, this can compute the gradient of the loss with respect to every parameter of the model, and storing each term in a PyTorch hidden state graph. So this means that by just calling this function in a one line, you are computing gradient of all parameters with respect to the loss function. And now we want to actually, in this step, we compute the gradient of the parameters with respect to the loss, and we want to update the network weights based on some optimization, right? So after defining the model, we need to define an optimizer that updates your parameters based on some formula. The simple formula that I show here is actually the simplest one that I know, but there are lots of other functions that we call them optimizer to update the weights that we have in the networks. So we need to define an optimizer, and then after defining that, we call a step function on an optimizer to update the model parameters. And it's also important to compute the gradient at the first, which means that we need to compute the gradient by this line and then call a step function to update the parameters. Because if we don't know about the gradient, how we can actually update the parameters. So there are lots of optimizer that are defined in the Torch, and you can have access to them by a module that you have in the Torch, torch.optim, and then you can call a function that you want. And one of the best optimizer these days that most of the people are using is the Adam optimizer. And it doesn't matter, but that if it's based on the task that you choose this optimizer, but in most cases, Adam optimizer are getting best result. And for using this function, you need to pass model.parameters parentheses and then one actually learning rate to this function. And this is because in this formula, you need to have a learning rate, and you need to the parameters or rates of the network to compute this actually the updated weights for each parameters. That's actually that's why we are passing model parameters to this function and also the learning rate. So you can define the learning rate here. And after that, we pass the input to the model and getting the output. And we define the loss function here. And we are using that, So we are using that here by passing the predicted output and the true output to get the loss function, loss values actually. And by calling this function, we are computing the gradient. And then after computing the gradient, we just need to call a function from the optimizer, which is the step, to update the model parameters. So if we apply this code in the previous slides and then continue to compute the loss over again and again and again to make it a smaller loss, actually we are updating the parameters by the gradient, and then we expect that we get a smaller loss because the model is learning something, hopefully. And also there's another important point here that we need to call a zero grad function on optimizer after each step call. So this means that we actually, if we don't call zero grad function, we are adding the each gradient in each step. So because we don't want to do that, and we want to get each gradient based on the current state, we need to call the zero grad function after each step to make sure that the gradient are zero at the end of this epoch. So for the training, at the first, you need to define a model based on, for example, using sequential nm.sequential. And you need to initialize layers weights that PyTorch can do that for you. You don't need to do that. And for each input-output pairs in the dataset, you need to feed the input to the model and get the output, and then compute the loss function based on the predicted output and true labels. And you need to call a backwards parenthesis to compute the gradient of the parameter with respect to the loss. And finally, you need to update the network weights based on these two functions, step and after that zero grad function. And you need to do that in a loop until the convergence or for a fixed number of epochs. I put an example from this this link here to show that how we can train just a simple neural network for you to have a just prototype. And you can also see these links for additional information. But let's see how we can implement just a simple neural network and train that on the PyTorch. So at the first, you import the torch and then torch.nn as an NN, and then we define some variables here, the number of inputs, the number of hidden layers. Actually, this should be the number of hidden units, not hidden layers. I'm not sure about that, but we find out based on the code. So this is the number of output which we assign them to 1, and then the batch size, which means that in each epoch how many data input you want to feed to the networks. And we have learning rate that we assign 0.01 to the learning rate. And for the input, we just define the actually here the batch size is the number of points that we have. So we just randomly initialize a matrix with the number of points and the number of features for each data point. And for each data point that we have, for example, here we had 100, we are generating a random number for the output. These two can be generated based on the data set. Because we are not using any data set here, we just randomly initialize them. And we define a model based on the sequential function. And at the first, we have another linear actually layer with the number of inputs that they actually are the number of features and the number of hidden that we want to have. For example, we are downing 10 number of inputs to 15, which is the size of the hidden unit, the size of hidden layer. After that, we are applying a nonlinear function on this hidden layer, and we are defining another linear layer. And after that, we are applying another nonlinear function. So in this case, we have 2 hidden layers. And for each one, we have a different nonlinear function. So after defining the model, we are defining our loss function, which is the mean square loss function, same as before. Here in example, we actually this link use another optimizer, which is the SGD, and then get the parameters of the model and the learning rate. Before that, we use Adam optimizer, but you can use lots of other optimizer here based on this module in the torch. And so now we define the model, we define the loss function, and we define the optimizer. So how we can compute the loss function? Here we have 5,000 epoch that we are going to applying the input to the output and getting the loss, and then compute the loss function and update the parameters of the model. So it's completely dependent on you and the performance of the model to define the number of epochs in your model. For each epoch, we are applying the input to the model and get the predicted output and compute the loss function based on the predicted output and then the true labels that we have and they are expected in the output of the function. And we get the loss. And for calling loss, if we want to know that what is the value of the loss, we just need to call a item function from the loss to get the exact value of the loss function. And I define a list for storing the loss that we are getting for each epoch. And I just append this loss function to this list, right? After that, we need to make sure that the gradient are 0. And after that, we compute the gradient of the model, actually the parameters of the model based on the loss function. And then we call optimizer.step to update the parameters of the model based on this gradient. So also there is another based on the math that we already seen. We can just I'm sorry. We can actually we can plot the loss function based on the epoch. Here you can see the number of epochs and the loss function for each epoch that we are getting. So we just need to pass this list that we generate here, and we define a label for the x-axis and x-axis, and then the title for that, and then plot.show. As you can see, at the first, the loss function is so large, and then based on the number of epoch that we are getting, smaller and smaller loss function, which means that the network is training to generate exactly the same output that we are expecting as a true labels. So this is another, I already explained that. So now you know how you define a model and how you train your neural networks on the PyTorch. I'm not going to detail of the GPUs, but with a few extra line of the code, your network can be trained on a GPU that it's so faster than CPU. For example, for a large neural network, the difference between the time in the CPU and GPU can be 1 day. That's huge, and sometimes you need just you can just apply your model and train on the model on the GPU. Running on a GPU actually can be so fast, and then training of the model is so fast for the GPUs. And also the GPUs are so good at performing many simple operations, and they can be actually done on GPU in a parallel ways. And matrix multiplication is a bunch of parallel simple operation. And because the neural network, as you saw, there are so many multiplication between layers and the inputs or outputs layer. So the matrix multiplication is so important. So because the GPUs can do that in parallel, that was so useful to run them on GPU. So if you define a huge networks, consider using GPU if you find a machine that have GPU. And to run a GPU, you must load your tensor and your model on the GPU device. This is so useful and easy if you want to use the GPU if you have a machine that has GPU. So if you want to do that, you just need to call the function device and passing these parameters to that, and then you load your data, and then you define a model based on the sequential or any other function. And at the end, you just need to call a training data that we defined here to the device that we defined here. And also you just need to pass the device to the model and then train the model. And that's the easiest way to run your code on GPU. And if you want to running your code on GPU, you just need a computer that has a CUDA enabled GPUs, and many laptops that we have cannot have GPUs or CUDA enable that, but Google offer access to one GPU at a time in a Python network Colab, if you already heard about that. And in this link, you can just get one GPU at a time by Google, and might your department or advisor have access to GPU? You can ask them if they have. In computer science department, we had GPUs on Gypsum machine, and which is the computing cluster of GPUs. And these days we have another one, which is the Unity. And if you are in computer science department, you can use them. And there are lots of other library in PyTorch that actually provide state-of-the-art models for specific domains. For example, as I mentioned, for the NLP, natural language processing, you can access the transformers networks that are generating most useful output for this task. And for graph neural networks, you can use deep graph libraries from this link. And there are other implementation in the PyTorch that can be so useful for some task. For example, in you can actually find them this useful implementation in the PyTorch in this link. And but I encourage you to actually find the implemented code in your task on the web before trying to implement them by yourself, because they are more accurate, and then you can use them and just adjust them to your task. And there are a few other PyTorch alternative out there. The most famous one is TensorFlow from the Google. That another one is therefore, I think this is therefore Microsoft. But based on my experience, the PyTorch is actually is the easiest way that and has a most friendly interface to implement codes in the Python, like actually in the for the deep neural networks. And this